Yeah, welcome everybody. We are very thankful that we can give here a short presentation. I'm David Pommerenke. I'm professor at the Graz University Technology in the Institute of Electronics, and this is my colleague Jan Hansen. He's also in the same institute. We work on EMC, electronics, antennas, and antenna propagation. We have been cooperating with Oguz University since 2023. Our talk today is about electromagnetic compatibility, and our example is automobile. Here we have a drive system from a BMW, an electrical BMW, and you see you see all the drives and transistors, and all the switching elements cause a lot of electromagnetic noise. And the noise can disturb radio reception, the noise can disturb other functionalities like airbag in the car, and so the noise needs to be filtered very well. And filtering is done with such a filter. This filter is rather heavy and expensive. And the goal is, of course, always for automotive industry to keep functionality, but reduce price, reduce size, and make it ready for mass production. Now, the artificial intelligence allows to do a multi-phased, simultaneously optimization, and Jan Hansen will explain.
Yes, so in order to train a machine learning model, we need many model evaluations. And usually we do this with computer simulation. So here you see a circuit model of such a traction inverter. So you see the B6 bridge, you see a machine model, and you see the filter. There's one part of the filter here, there's another part of the filter here, and here there are some elements to measure the conducted emissions of the noise. This model can be quite complicated. It represents a CISPR25 conducted emission setup, and it has about 2,000 distinct circuit elements. And out of these 2,000 elements, we can choose the interesting ones which determine the filter performance. So we see here there are certain parameters which determine the properties of the AC core. There are certain parameters which determine the properties of the filter, and there are also parasitics like the ground inductance or certain parameters of the control sequence of the inverter. And we can choose these parameters as free parameters and train a machine learning model on this. Once we have done this, we can do wonderful things. For instance, we can solve multi-objective optimization problems. EMC is a constraint. You don't build an inverter with having a particularly good EMC. What you basically want is you want to build inverter or traction inverters for automotives which have high performance, which fulfill certain thermal criteria. And EMC also has to be fulfilled. But you cannot optimize all three, you cannot drive all three of them into an optimum. Usually you are looking for trade-off solutions. And how to find such a trade-off solution is usually done using Pareto optimization, where you have certain design parameters. In this case, it's the volume of the common mode choke, which is an important filter element, and it's the volume of all the filter capacitors that we have. And you can optimize, you can look for optimal samples which are on the so-called Pareto front, which are either the ones which have a small common mode choke or the ones which have small CY capacities, but you can't minimize all of these elements. So the optimal choice of the designs is the so-called Pareto front, in which you have the combination of the smallest possible common mode choke and the smallest possible CY capacitors. If you run such an optimization, we end up with a pretty high dimensional space. So in our case, our filter and the entire system has about 15, 18 different parameters. And in order to navigate an optimization through all these parameters, we are using a quite subtle strategy. So we have some linear objectives which we try to minimize, for instance, the filter elements. But we also have our EMI constraint. So we have to pass the EMI rules, the EMI limits of the system. And then we have some functional parameters which we run through on a grid. And studying all these parameters in details is possible because the ML model runs incredibly fast. The model we have trained here on such an inverter allows us to screen several millions of different samples per day. So we can run through all these parameter settings in a certain scheme. And what we are going to get out is a so-called scatter matrix. In this scatter matrix, we see all the design parameters of our system, like CY capacitor size, CY capacitor parasitics, or length of the common mode choke. And we see all the interrelations between these different parameters. So for instance, we can observe that if we increase the size of a CY capacitor, the size of the common mode choke decreases. And such a table is extremely powerful because it shows us all the correlation between the different design parameters. We want to learn and understand if we improve one of the many design parameters, what happens to all the others. Do they become also better? Do they become worse, which is most often the case? Or are these parameters not related? And the machine learning model allows us to derive such a scatter matrix and to study all these correlations between the parameters. And once we have these parameters, we can choose optimal points and end up with tables of design parameters. Here we have three Pareto optimal solutions. One is the solution where we have the minimum of the common mode choke. The second is the solution where we choose all the capacitors of the EMI filter to be minimal. And we have a trade-off solution where we sort of balance the size of the capacitors with the size of the common mode choke. The common mode choke is a very expensive parameter, and this is why we look a little more closely at its values. And we see here that the optimal solutions, they allow us a variation in the size of the common mode choke, which is pretty much a factor of 5. So screening all these parameters using our machine learning model allows us to find many, many optimal solutions which fulfill the EMI constraints and which allow us to screen systematically sets of design parameters that we like to choose because they are good for us in sense of cost, in sense of weight, in sense of mechanical realization. And here you see that all these three parameter settings that we have, they fulfill the EMI limits. So we do not have only found a good setting of different parameters, but we can guarantee by the design of our model, by the design of the optimization run, that all of these solutions that we have do fulfill the EMI limits given by the EMI standards of CISPR 25. That concludes my short presentation about the application of AI and ML in EMC design using the example of minimization of a filter of a traction inverter from automotive industry. If you have any questions, please email us. David and me are ready to answer all your questions. You just put them in an email and we are happy to reply.
And we only had a short moment, so in the short moment we could not explain all the technology or mathematics, but I hope we could make you a little bit interested to dig deeper into this area of electromagnetic compatibility, which is really good to apply artificial intelligence to.
You're the signal in my static hum, a perfect match we've overcome. Wires cross but we still